Hey everyone, thanks for tuning into this demo. This week is a little bit unexpected because the lecture ran over. So instead of talking about visual transformers or transformers, we're going to be talking about object detection. This is particularly relevant because basically what we'll be talking about today is a homework problem. You'll just have to do something slightly differently. So I hope that you find it useful. Our task is to do object detection. Particularly, we're going to be considering the problem of doing this on people. So for example, given an image that looks like this of a bunch of people walking, we're interested in producing two things. The first thing is that for each person, we want to put a bounding box around them. That's these like red little things that you can see. Um, and the bounding box basically contains the object of interest, which is the person. So it doesn't work so well here because this guy's hair is getting cut off, but for these other people, it does work quite well. That's the first thing we want to produce bounding boxes for the object that we're interested in. And the second thing that we want to produce is a segmentation mask. A segmentation mask is just something which is the same size as the image that we're working with, so it's the same number of pixels and it consists of zeros and ones. Zeros represent that it's not being highlighted and ones represent that it is being highlighted. So here we're mapping each one of the ones with blue. So it looks like it's picking up that this is a particular person, and each one of each part of them, each pixel that it thinks is part of this person is appearing as a one here. And we have this for each one of the people in this crowd. Of course, this process becomes very difficult when we have a large number of people, a large crowd. So it breaks down over here with this math of people. Okay, so that's our task. We want to do object detection, and we want to put a bounding box around each object, each person, and a segmentation mask, which outputs a one if the person is, or if if the thing is the object, and a zero otherwise, if the pixel is the object. Okay, so object detection is very difficult and frankly annoying because you need to consider lots of different parts of the image, and you also train for several losses simultaneously. So because of that, we're not going to be doing basically any of this from scratch. We're going to be using a PyTorch tutorial, which is described here, which is given here, and I just slightly edited it so that it's simpler to understand for our purposes. But we'll be explaining some of what's going on in this. Okay, so the image that we work with will be our normal size image. We have a color image, 3 channels with the height and width given by h and w, so it should be a tensor of size 3 times h times w. The target is a little bit different than what we're normally used to working with. Normally, we're used to working with just one thing. Here, we're going to be working with several things. The first of them is a bounding box, which defines where the object appears. We're going to specify the bounding box by the bottom left coordinates and the top right coordinates. And those 2 points, we just draw the right box given those 2 coordinates, and that'll give us a bounding box. So in our data set, we have an image, and then someone has come through and given us a bounding box of where the objects actually appear. We're going to have labels. In our case, we're only interested in doing 0 as a background class and 1 if it's a person. But you could think about a more general task where you have images of different or animals, and the goal is to not just detect where each animal appears, but also what type of animal it is. The other thing that will be interesting for us is the masks. The masks are the segmentation masks. Notice that this is the same dimension as our image, so it's or the same number of pixels in our image, which is height by width. And n here is the number of people that we see. So we're going to have a different mask, segmentation mask, for each one of the people in our image, and each one of those masks will be the same size as the image, and it'll just consist of zeros and ones, determining whether or specifying whether the pixel, if it's a 1, the pixel is on the object, and if it's a 0, it's not on the object. There's also a few other things, this image idea, area, and crowd, and those will just be useful in a way that we won't talk about and will be abstracted by the classes that we're using. Okay, so that's what our data set consists of. We're going to be using a custom data set, which is called Pen Fudan. Pedestrians, PED. You can download it by clicking on this link. Once you download it, you can unzip it, And then if you're working with Colab, the thing that I did is I re-uploaded it to my drive in a folder called data. And then within data is this data set that I unzipped from that link. As you'll notice, there are the three things that we care about. There's the image itself, there's the segmentation mask, and the annotation, which specifies where the bounding boxes are. Let's take a look at one of these images, image 96. Here we have a picture, and in the picture there are two people. A few more, but I think it would be very hard to classify them, so they're probably not in the ground truth label. Here again, we have a different image with two other people, and so on and so forth. That's what appears in this data set. Notice that the image sizes are different. This is a very nice feature of the particular models that we're going to be working with. It doesn't matter the shape of the images that we're going to put in as input, and we'll talk about why that's so useful and so cool in a second. Okay, so this is the image that we're working with. Let's go back and look at the annotation. We'll also do that for image 96. Here, basically this is saying that there are two objects. There's a person walking and a person walking. For the first pedestrian, we specify the bounding box around them. So this is the bottom left coordinate, and this is the top right, or bottom left point, and this is the top right point. And together they specify the bounding box for that person. And we have the same thing for the other person. This also tells us where the segmentation mask is. So if we go into that folder, ped masks, and we look at 96, this is the segmentation mask for that person. Because it's 0, 1, and we're probably trying to load this with an RGB value between 0 and 256, everything looks black, but we'll be able to process this data ourselves. Okay, so that's what the data set consists of. We're going to specify a custom data class loader or data set. The thing that we do is we tell it where each one of these images and the masks are. And for a particular image, when we want to load that and the targets, we're going to load the image, load the masks. We have special functions for reading each one of these things. And we're also going to do two important things. The first is that we're going to get a mask and the bounding boxes, and we'll make sure that they correspond to each other. Here with the labels, there is only one class, so this will just always be one. And then we define all these other variables that we talked about before, and we return these things. So in the case of the bounding boxes, we're getting the bounding boxes from the things that we defined here from the boxes that correspond to each one of the masks. We get our masks, the labels in each one of these. I will scroll down briefly so that we can just take a look at what each one of these things looks like. So if we define images, images, the thing that we're getting from our data set, our data loader, is a list. If we look at the first one of them, and we take a look at its shape, we'll get some shape for it. So it's a color image, and the dimensions are 487 by 493. Notice that this is different between our images, so our model will be able to handle different size images as input. Let's also take a look at our targets. It's also a list. Let's take a look at the first one. This one has the different objects that we defined in the data set. So that's boxes, image masks, labels, image idea, area is crowd. We'll be particularly interested in these two things. Notice that there are two bounding boxes. So this indicates that there are two people in this image, and we have a bounding box for each one of them. Let's look at the masks. And this will be a tensor. If we look at the shape of this is the number of pixels in the image, so the height and the width, and then also two because there are two different masks that we care about. If we look at a different image, look at 3. Oh, this targets could be very small. Okay, that's interesting. So, okay, I guess there are only two things here. Notice that the number of masks we have is different because that's a different number of ground truth people in our image, and the dimension of this image changes as well. And that's something that we're able to handle, and the dimension of the mask is just the same dimension as that of the image, but we have several masks, one for each one of our people in the image. So that's what our data set looks like. Let's talk about the models that we're going to be using. The first model that we're going to be using is something called Faster RCNN, and it does something clever, which makes the object detection process faster. It's definitely not fast, but it is faster than other approaches. The thing that we start off with is we take an image and we apply a deep convolutional network to it. Notice that because we're applying convolutional network to it, it doesn't matter the size of the initial image. We're just going to get a rich understanding or rich representation of what's in this image. With this deep representation of that image, we'll consider different subsets of that representation corresponding to different regions of interest. That's what ROI stands for in the starting image. So for example, let's consider one region of interest, which is this cowboy on a horse. That corresponds to a particular subset of our deep representation of the image after we apply the convolutional layer. And one thing that makes this fast is that we only had to apply the deep convolutional layer once. And when we look at this particular region of interest, we just take that subset from our deeper representation of it. Once we have that subset corresponding to this region of interest, we want to make sure that it's the same size no matter what. And we can do that through a pooling layer. The pooling layer will basically add some padding to it, add some zeros, so that no matter what the dimension of the region of interest is, the dimension of our pooling, our representation after the pooling layer will always be the same. The reason we want to do this is because the regions of interest will be different sizes. So in this case, this is an image where the person takes up basically the entire thing. But if we had a different image with lots of people in it, each person would take up a different size in this shape. So for example, in this image, there are several people in this image, and we need a region of interest for each one of them. Because of that, there are going to be lots of regions of interest, and each one of them will be in a different position on the image and a different scale. Because there are different scales or different sizes, it's important that we make them somehow to be the same size before we apply our fully connected layers to them. Right, okay, so we do this extraction for each one of our regions of interest. We do a pooling, so the size of it is the same. We apply some fully connected layers, and then we want to output two things. The first thing that we output is what is the probability that this region of interest contains an object that we care about. In our case, it's people. And the second thing we want to output is a bounding box of the most likely object that was contained in this region of interest. This is a regression process because we want to fit, we will have some candidate for what the bounding box would look like. So where these different top left and bottom right point, or sorry, bottom left and top right points are. And we can do regression to try to get them as close as possible to the true target bounding box. Notice that this also is a place where we gain speed up in this algorithm because we can take one region of interest, and within that region of interest, we can fit several different bounding boxes corresponding to where the object actually is. So this makes it faster because we don't need to do a different processing step for each one of the bounding boxes that we have. Okay, so that is very cool. And a side note of this is that, or a side benefit, or a positive externality, is that it doesn't matter what the dimension is of the input size, because no matter what the dimension is of the image, we can apply this convolutional layer, we can select out a region of interest, and whatever size that region of interest is, we will do this pooling operation so that we'll get it to be the same representation no matter what that size was. So we will be able to fit in or feed in different sized images into this model, which is very exciting. The whole point of this faster RCNN, this thing in gray back here, is that we will be able to output for this region of interest. The softmax operation gives us the probability that this contains an object that we care about, and then the regression operation or regression loss here would give us a bounding box that hopefully contains that object. Okay, so this will give us bounding boxes. We're also interested in a segmentation mask. For the segmentation mask, we're going to use a different model called mask RCNN. And the idea here is similar. We're going to have one deep convolutional layer, which will take in our image and produce something of a similar size, which has features for each one of the pixels of the starting image. Then based off of that, we're going to look at different candidate regions of interest. This time, for each one of our regions of interest, we'll pass it through a convolutional layer. The convolutional layer, one thing that we can do is output like which thing what thing do we think this actually is? In our case, that just corresponds to like, is this a person or not? But it could more generally be what kind of animal is this? And this convolutional layer keeps the size of the region of the interest the same. And it just tells us in this region of interest, if there is a person, where would that person be? And this is a 0-1 prediction of whether this person is in that like particular pixel or not. We train this part also with cross entropy loss because we want our image predictions of where our segmentation mask to basically fit a binary label of is this pixel part of the object or not. Notice that one way we could have approached this is just applying these convolutional layers to the entire image. But in that case, we lose out on getting, we are forced to solve a harder task, which is given this whole image with all of these different people and trees and different objects going on, where is this particular pixel part of a person or not? And that's a very difficult task. We make this task easier by just considering different regions of interest. And hopefully the region of interest only contains local information around each one of the people in the image. And by defining it in this way, we are able to solve the problem better because it's a like more simple problem that we're solving. Okay, so given the setup and something that produces segmentation masks and bounding boxes from an image, we could just run the pre-trained model, or we could try to modify it. One way that we can modify it is just replace the last heads. So we can replace this last part of the process, the different convolutional layers, which will actually give us the segmentation for each region of interest. And this, the like different pooling layers and fully connected layers, which gives us the bounding box and the softmax layer. That's one thing we could do. Another thing we could do is also replace the backbone of this task, which is how we go from the image to the steep representation of it, how we go from this image to this steep representation of it. The first option, just replacing the heads, is what we're going to do in the demo today. Your homework problem is to replace the backbone. And there will be code that will help you with it if you scroll up to the top and follow the PyTorch tutorial, which this is based on. Okay, so we're going to do the second one of these things, which is modifying the heads on top of it. The way we'll do that is we'll load this pre-trained model, which is called a mask RCNN resonant 50 FPN. And from this, we're going to do two things. We'll, I think, replace the box predictor with our fast RCNN predictor, which is the thing that we were describing up here. And then we'll replace our mask predictor with a mask RCNN predictor, which is this thing right here. Okay. And we just want to, we did a very similar thing before when we were working with residual networks. We just want to make sure that the dimensions of this all make sense. So in particular, we need to get the right number of features that are being passed in here. And that'll just be the input to the like final predictor that we have. We also specify the number of classes. In our case, the number of classes should just be 2, which is this a background thing or is this a person? Okay, so that's the way we define the model. We do the first of these options. For the homework, your job will basically, or the homework problem 5, your job will basically be to replace them. Okay, now that we have defined our model and we have our data set, we'll put everything together. This task is very difficult and there are lots of hacks that make bounding boxes work. Unfortunately, that means that there are lots of different functions that we'll need to do, or we'll need to use. We won't define all of them here because it would be a very painful process. So instead, we're going to download them. When we download them, they appear here in these different files. So for example, in the engine file, this is a Python file and it defines the training process that we're going to do for one edit. We will abstract all of this away because if we try to understand what's going on, it'll lead us down a very long dark hole where it'll reference all of these different objects and things all over the place. So I don't want to go through that. And in part, that's why bound object detection is a somewhat difficult and perhaps even annoying task because it's difficult, that we need to do lots of hacks, and you wouldn't want to code it up from scratch. So we rely on lots of work that's already been done, but that makes understanding this at a detailed level very difficult. At this step, this enables access for our data set to Google Colab. If you want to use this exact file path, just make sure that your data appears in My Drive. So you have the same file structure I do, which is that you put this data set in data, which is in your My Drive. And if you set it up that way, then you can just use this, or if you set it up a different way, you can redefine this file name. We're going to define the transform. The transform is a thing that we apply to our image. This we've been doing before, where we just take in each one of our images and we process it in a way that like makes maybe the distribution nice or some other aspect of it nice so that we can pass it into our image. We defined our, here we're just going to define the model without replacing the head, and we're going to see that everything works. We'll load our data from from our data loader and our data set that we gave it access to. And we can look at what the dimensions are of these predictions. So if we look at predictions, this will be a list. If we look at the first thing in predictions, this is something that's a bounding box, labels, scores, and masks. Notice that when we looked at the actual targets here, it was a completely different dimension. Like the number of bounding boxes we had was very different. So initially, this is based off of a newly initialized layer. Oh, actually, this might be the full thing. I'm not sure. Okay, but the thing that we're getting from our bounding box from our predictions is the same shape as our targets, or the same type of object. We have bounding boxes, labels, scores, and masks, and yeah. And for each one of these, we'll apply a different loss. For the bounding boxes, we want to make sure that the points are close to the actual ground truth label bounding boxes. For our scores, these contain the probability that each one of our images has, or the probability that each one of the objects, or each one of the bounding boxes contains an object that we're interested in. This will be trained with cross-entropy loss. Then we also have the mask, which is 0 or 1, depending on the shape of our, or depending on whether a pixel is in our object or not. And we also train this with cross-entropy loss with respect to the actual images. The reason this prediction is so large is because I actually redefined predictions later on. I don't want to rerun this because this takes a while to run, but you can just believe me, hopefully, that this is the type of output we're getting from our model. Now we can actually do the training step. We're going to redefine our model using this function we defined with an instance segmentation, where we apply both the we put in the new heads with a faster RCNN and the mask RCNN. We can define our data loader, and we also do something called a learning rate scheduler. The learning rate scheduler, the idea here is just that instead of keeping a constant learning rate over time, we vary it. Now this is useful because if we're close to a local minima and we want to get out of there, we probably want to try increasing our step size. However, if we're close to a minima, or we're not very close to it and we want to get closer, maybe we want to try decreasing our step size so that we make sure to fall into the right minima. There are lots of different theories and basically heuristic approaches on how to choose a learning rate scheduler. Here we're going to do a very simple one, which just decreases the learning rate over time, with the idea being that at the beginning we want to take large steps because we hopefully want to get close to a region with minima, and then over time, as we have been training for lots of epochs, maybe we want to decrease the size so that we make sure we optimize for the particular minima that we found. We can run this process using the train one epoch, which was defined in one of the files that we loaded. I don't want to look at the particular code for that because, as I mentioned, it's incredibly gross and relies on lots of different things, in part because of the nature of object detection. We do lots of training steps. In the evaluation step, we look at the IOU metric, which is the intersection over union, which is how close is the bounding box that we're proposing to the actual one. And hopefully over time, the the IOU, the metric that we get, increases. And that's exactly what we see as we train for more epochs. Generally, on average, these values increase, indicating that our bounding boxes are more accurate. After we finish this training process, we can visualize and look at what a particular image will look like. So we can look for people walking, let's say. You can try this yourself. You can choose whatever image you want. Clearly, the one that we were looking at earlier is just something that appeared here. Ooh, actually, a fun one might be the Beatles cover. Okay, nice. So we can try plugging in this image and see if we get the right the silhouettes around the Beatles. So we go back, we can just replace this URL with the URL that we just got. We run this process and we can run this down here. We'll be passing it through the model. When we get out our predictions or pred, it should be the same type of object we had before. So we have bounding boxes, masks, and labels. In our case, we just care about the bounding boxes and the masks. The bounding boxes it gives us, this is not particularly, I don't know, it's the wrong number, right? Because there are 4 people in this image, but it's giving us, it looks like 8 different bounding boxes. And it should be the same thing for each one of the masks. So if we look at masks shape, it should be 8 by whatever the dimension of this image is. Okay, so let's scroll down and plot it to see what's going on. Interestingly, it looks like it did very poorly. So it looks like there's one bounding box here, one bounding box. So it looks like it gets to the right bounding boxes, but it's also producing ones that are not very helpful. That like superfluous ones that are over both of them. Interestingly, now this is very impressive. It also recognizes this person as a silhouette and puts a bounding box around them. Part of this could be that maybe it's not used to like people walking with their legs this far apart. So maybe we can try a different image. It's cute. And see how well this does in terms of the segmentation mask and image and bounding boxes. Okay, so this looks better. Again, it looks like we're predicting too many bounding boxes, but the segmentation mask looks very accurate because each one of these people is getting a segmentation mask around them. It looks like the umbrella might be messing them up, but that's perhaps to be expected. We can try, I don't know, just other images of your choice. We can do one that's easier. This one should be fairly easy. And hopefully the number of bounding boxes is ooh. That's interesting. Cannot identify image file. Okay, so maybe there's something with this image that let's just try a different one. Okay. We could also the nice one. Ooh. This one hopefully it does well on. And it runs, excellent. And when we plot it, cool. Okay, so it looks like it does well. It identifies each one of these people in this very toy image example, but it's also giving bounding boxes around it. Hopefully the thing I want you to take away from today is that one, object detection can be very cool. It's awesome that we can just take a random image from the internet and get a result like this. But at the same time, to make this work, there are lots of hacks that go into it. One thing we didn't discuss is how it chooses different regions of interest. It's important to choose different regions of interest. There are different scales depending on how big the object actually appears in the image and the different positions in the image. To do this effectively, you need to consider lots and lots of regions of interest, which is why running this model takes a while, unfortunately. And then the other piece of this too is that you're not just training for one type of box, you're training for several. So you simultaneously want the bounding boxes to be close to the true bounding boxes. You want the score of the bounding box to be close to the actual probability that the bounding box contains a person. And you also want the segmentation max to be right, and you can train that with cross entropy loss. To make this all work, there's lots of stuff that's going on under the hood, which is quite painful, but I think given the demos that we've had so far, you're able to, at least at a high level, understand what's going on. And if needed, you can always dig into the documentation to get a better sense of that. Thanks for tuning in. Next week, we'll be talking about transformers and in particular, hopefully visual transformers. I look forward to having you there then. Bye.